In my first binomial video, I showed you how we identify whether a binomial probability distribution exists or not. The question next is, what do we do now? Good thing you tuned into the second video. Let's go.
Give me 6 minutes and I'll teach you something new. Now, let's get to work.
Hello again, Mark here from 6 Minute Statistics. Thank you for coming back for this second binomial video. Hopefully you've already figured out how to identify binomial probability distributions, and we're going to move forward from there. But before we do, could you do me a favor? How about liking this video and or subscribing to my YouTube channel? I got some big dreams and visions for this channel, and I really could use some support from you. Thanks. Now, let's go back to the smoke detector example I was working on when I introduced the binomial criteria to you. I'm going to put a link in the descriptions in case you haven't watched that video yet. But in this video, we want to move forward. In that example, some firefighter friends of mine told me there was an 80% chance that a house has an operable smoke detector. And they sampled 20 houses from the area in which they are firefighters. Suppose they want to know the probability that more than half of those 20 homes have operable smoke detectors. How do we work that problem? Well, we've already identified that it's a binomial. We said it's a binomial with n equal 20, and P, the probability of a success, and a success was defined as a home having an operable smoke detector, that P was equal to 0.8. We defined X, a random variable, to be the number of homes in the sample that have an operable smoke detector. So the second step, the first step is identifying you have a binomial. The second step is trying to figure out how do I write what they're asked to find in a language or using some symbols that the binomial distribution can be applied to. And so how do I rethink about more than half of the homes? Well, in a sample of 20 homes, what's more than half? 20, half of 20 is 10. What's more than 10? We're going to write that probability as the probability X is greater than 10. And then we're going to solve that probability using some tools I'm going to show you about in my next video. What if my friends wanted to know the probability that less than 5 of the homes have operable smoke detectors? Well, using the same kind of thinking, we're now going to use the symbol, if less than 5. How many of those homes have an operable smoke detector? That's X. We're going to write that as the probability X is less than 5. And now I'm going to make that, I'm going to turn that into the probability X is less than or equal to 4. Can I do that? I can. Because we're working with a binomial, we know the values of X have to be the whole number, 0, 1, 2, 3, 4, 5, all the way up through 20. So if you want to know the probability less than 5, the only values of X that are less than 5, I could also write as less than or equal to 4. Weird, right? It gets worse. Look at the way I'm going to write the probability X is greater than 10. Remember, more than 10 that we looked at just a second ago? I can also rethink that as 1 minus the probability X is less than or equal to 10. And I know you're probably thinking, what just happened? I'm pulling out the secret ninja statistics tricks. Not really. You know 2 rules exist with random variables, or at least you should know that. All the probabilities have to be between 0 and 1. Most people remember that one. And then the second rule is that the sum of those probabilities have to sum to 1. The sum of all the probabilities has to be 1. So to help you see this maybe a little bit more clearly, I'm going to put some dots on the screen right now. And those dots are going to represent the different values of X. So not only are they dotted, but there's also going to be labels for X. So you see the 0 dot, the 1 dot, the 2 dot, all the way up through the dot for 20, because those are the values for X, the number of homes that could have operable smoke detectors, 0, 1 through 20. You'll notice there's 21 dots. If I wanted to take a picture of more than 10, more than half, right, greater than 10, I could draw a rectangle around the dots that would include 11, 12, all the way up through 20. But if I drew a rectangle around all the dots, not just 11 through 20, but 0 through 20, and looked at the probabilities involved with all those dots, all those values of X, we recognize that that has to sum to 1. So I have the 1, and then I got the probability X is greater than 10 that I'm interested in. What about the other part of that? What about the other rectangle, the rectangle that includes the values that aren't greater than 10? In other words, the rectangle that would include 0 through 10. Notice the 0 through 10 rectangle and the 11 through 20 rectangle make up all the different outcomes of the entire rectangle. So another way of thinking about greater than 10 is it's equal to 1 minus the probability x is less than or equal to 10. Pretty cool, right? How about if I asked you the probability x is equal to 15? What's the probability exactly 15 of the homes have operable smoke detectors? Well, I could draw a little rectangle around the value of 15, or I could say that's the probability x is less than or equal to 15, look at the box I'm drawing, minus the probability x is less than or equal to 14. Some pretty serious statistics tricks going on here. I'm using the dot diagram. In fact, I think I've invented the dot diagram. I've been using it for decades. I call it the Dummel-Dinger dot diagram. Pretty fancy, huh? Why am I doing it? What's the point? Well, it helps you to visualize what I'm asking you to find, but more importantly to that, it looks at it in terms of less than or equal to probabilities. Notice what I've done. I've taken the more than 10, I've taken the less than 5, I've taken the equal to 15, and I've rethought or rewritten those problems all in terms of less than or equal to, or what I'm going to refer to as cumulative probabilities. Why am I doing that? It makes it look more complicated. It does. But here's what I know, and you're going to find out. The third step is going to come back and look at some binomial tables, or more likely, some binomial probabilities using computer software. And every single table, every single computer software package I've ever seen will be able to work with less than or equal to probabilities. For now, get in the habit of trying to rethink some phrases, some words in terms of x's. I'm going to leave some examples on the screen for you to try. And then when we get together again, we're going to take a look at some binomial tables and some software programs. Until then, it's time for you to get to work. So long.